So let's start. Thank you all for coming here today. I'm going to present about neural networks. Here I have what we're going to discuss, an introduction, what is a neural network, what is a neuron, how do they learn, a little bit about convolutional neural networks, and some applications. First, the introduction. Here we have an image of a number 3. Actually, there are 3 images of numbers 3s. And we as humans, we know that's a number 3, right? We just see it and we see that's a 3. But the pixels of each one of these 3s, it's different. This 3 here, for example, this pixel is here in, and this pixel here is not in. So the problem is, we as humans, we know how to identify these numbers here, for example. But how a computer can classify these numbers? For example, if I have a lot of photos with numbers from 0 to 9, how a computer can classify these numbers? This image here, it has 28 for 28 pixels. Each pixel holds a number that is the scale of green of the pixel. For example, 0 from black and 1 for white. And that's what composes this image of this number 3. A way of trying to solve this problem of classifying numbers with the pixels are a neural network. It's a neural network because it's inspired on the human brain. We have here this circle that are the neurons, and all these neurons is connected with each other. This connection, this position of the neurons in layers is like that. Just I don't know why it's layer. You can actually do other connections, but what we are going to do to solve this specific problem is with layers. So, actually, what is a neural network? A neural network, for example, I have this number 7 here. I told you it has 28 for 28 pixels of length. So there is 784 pixels. I can take this inputs in this first layer, and it will do something, some calculations, and it will get us a output here with the number of this input. For example, for this one, the answer is 7. So this neuron here has to be activated for this input here. Okay, so actually, what is a neuron? This circle I have told you. You can think a neuron as a thing that holds a number. For example, each one of this, actually the first layer is not actually a neuron, but it carries a number. For example, for this number here, all of this black neurons here holds a number 0, and the white ones holds a number 1. Actually, on our first notion of a neuron, we can think of a thing that holds a number. But actually, here is the disposition of the layers. We have a input layer here, an output layer, and we can have hidden layers here. You can choose 1, 2, 3 hidden layers, and we can choose the number of the neurons in each layer. But now we are going to see what exactly is the calculations of this neural network. Here I have the 784 inputs, and each one of them has a connection with the other neuron on the other layer. And each one of these connections here carries a weight. A weight is basically a number, and the final answer here for this neuron is the weighted sum of these numbers. For example, the first neuron I multiply for this W1 here. The second neuron I multiply with this second weight here, and I sum it all, and that is the final answer of this neuron. But how I told you, these neurons carry for this case, a number from 0 to 1. And probably if you make this calculation here, the result of this calculation is a number greater than 1. So how do we put this final answer in this range for 0 to 1? That's why we use what we call an activation function. This is a common activation function. It's called sigmoid. Here is the equation of the sigmoid. It takes numbers. If your number is really negative, the output of the sigmoid is going to be really next to 0. And if the input is a really positive number, the output is going to be next to 1. So we can write the answer of the next neuron like that, a sigmoid applied on this answer of the weighted sum. But actually, you can see there is other number after you do this weighted sum. We can add that number called bias that still goes on the sigmoid function, right? This is one of the activation functions. Actually, there are others, but in this case, we are going to use this function. So actually, what is happening with inside the neuron? Here, it's an example, a numerical example with 3 neurons of input and 1 neuron in the output. 0.1, 0.2, 0.3 are the inputs. 3 to 1 are the weights. This number 3 is the bias. This 4 is the answer of the weighted sum plus the bias. And you take this 4, you take it's an input on the sigmoid function, and it gives us 0.982. So that's the number that this neuron carries on the other layer, right? So actually here, I told you have to do these multiplications and add this bias. And when we have a lot of neurons and a lot of connections, we can represent all this calculation with a matrix with all the weights, a vector with all the inputs, and a vector with all the biases. And this equation here represents what you have to do to calculate the number that the next neuron is going to hold. So, but how this network learns? Basically, what we're going to use here is called supervised learn method. That means you have a data set. For example, here I have 20 images and 20 images that are the inputs and 20 outputs. Actually, we already know this supervised learn method. We already know the answers. We know if we put this 4 here, this image in the inputs, what we expect is this 4 here. So what we have to do? We have to separate my data set in 2 parts. One part I will use to train the neural network. In the other part, I will use it to test if my network is giving us the right answers. Here we have a half-half division, but actually you can use more data set to train and less to test. But how exactly do they learn? In our first, to put our first input on the first layer here, actually I have to choose randomly weights and biases for each weights for each connections and biases for each neuron, just to begin the neural network. For example, if I enter this tree here in randomly weights and biases, it will give us this answer here. We can see here that the number 8 is whiter than the others, and this 8 is the answer of this neural network for this input. You can see that it's wrong, right? But what is your objective with this? What is our goal with this neural network? We can calculate called cost function that we calculate to give us a measure of the error. For example, here, the right answer should be this, 3 activate and 0 for the others. But I can calculate an error. This error I can calculate with this mean squared error. This is one of one measure of the error that we are going to use in this particular case here. And what do we do? Obviously, this colors here is actually a number, right? 0.43 for the first neuron, 0.28 for the second neuron. And we can calculate this mean squared error. We take this number here, we subtract it with this other one, and we square it and sum all the pieces of this neural network for this case. Actually, that's the expression of the cost function that we are going to use. X are the inputs, Y is desired output, f of x is the estimated output of this neural network, W is a vector with the weights, B with the biases. How I said, the objective, the goal here is to minimize this cost function or the loss function, but we cannot change the inputs, we cannot change the desired outputs, but we can change the weights and the biases, and changing these two parameters, we can change the estimated outputs, and then we can minimize the cost function. But how do we minimize it? If you have already studied calculus, you know that this operation here is called gradients. Here I have the definition of the gradient for 3 variables. Here I have a function with only 2 dimensions, x and y, and the graph in other z dimensions. Right? If I calculate the gradient of this function in some points of the function, it will give us a vector that points to the direction where the function increases more quickly. For example, if I'm here in this spot and I calculate the gradient of a function, it's there. I have to go there, and there I'm going up on the function. It's like that. But we want to minimize the function, so we have to go to the other direction. Right? Here I have, of course, for 2 variables, the gradient does not have that third component, and this is only for 2 dimensions. But in our cost function, we have a dimension that has all the biases and weights, so that the dimension of that case is like 1,000 or 2,000. I don't know how many weights is there, but okay. So after we calculate these gradients, this method is called gradient descent, and we have this learning coefficient here. So what that means, this learning coefficient. Our goal is to change these weights and biases to adjust the neural network. And I already told that if I calculate in some point these gradients, it will give us a direction. But I can take 1 step to this direction. I can take 10 steps for this direction. This learning coefficient gives us this, how far do I have to go in that direction. For example, if I start in that point, we can know that I give little steps in this direction, and I probably will descend this function until I find the minimum, the local minimum of this function. So that's the process. We actualize these weights and biases to minimize this function. But there is some methods of doing it. The first one here is stochastic gradient descent method. We have here a training data. In our case, it was 10 values of training data. So for each one of the data, I have to calculate the 0 and change all the biases and the weights, and I I do this until you're finished your data set or until you want. But there's other, for example here, a batch method. We can calculate error only after passing all the data sets for the neural network. And we can combine the two of these methods as GD and batch. It's called a mini batch. We subdivide the data set in parts, and only after, for example, this 20 data set, I calculate error and actualize all the biases and weights. And for example here, and that's it. That's some methods of doing these actualizations on the weights and biases. Now a little bit about convolutional neural networks. This is other mechanisms of, it's more used in images. First of all, we need to understand what is a convolution actually. Here I have an image of 64 for 64 pixels, and I have this kernel here. This kernel here, it will, for example, in this corner here, I have to multiply all these values of the image with this kernel, and it will give us a output that is 1 pixel here. So if I multiply here, I multiply this corner here with this kernel, I have this 31. So if I displace this square here for the other spot here, I will have this output here. So that's what the convolution is. We pass this kernel on the image, and it will give us another image as output. You can note here that the input has 64 for 64 pixels, and the output has 62 for 62 pixels. This is why when we choose the size of this kernel, we lost one dimension in each side of the image, right? So what happens in a convolutional neural network is similar to the neural networks with the neurons, but actually what we have now is these filters here. Actually, in the neural network with the neurons, we learn the weights and biases, and here we learn the filters. These filters here. For example, here, if we have a colored image, we need to have three filters, one for each RGB, red, green, and blue colors of the image, and we can pass for these filters and pass for other functions until we have an output. We can make this error loss function and actualize all these parameters of the filters, and that's what actually is happening. But now with the convolution, not with multiplications and sums. Here is an example. I have an input image. I do this convolution here, and I pass it for other functions. For example, this pooling function. It gives us in this kernel here, for example, it will give us the higher the pixel that has a more expressive weight. And basically that's the difference. Here we learned the filters, and the other case we learned the weights and biases. Right. Now some applications of neural networks. For example, we can applicate it in facial recognition. For example, if I take pictures of all of you in this class, and I know that's a picture of you, it's Pedro, a picture of Diana is Ana, and I can make this thing is subdivide my data set in a part of training and test, and I can learn this actually for facial recognition for images. In general, we use convolution, and our neural network is going to learn how to classify these persons, these people, and you can do The same thing with other images, flowers, cars, but that's the same process. Another application is for stock market prediction. Actually, if you see this graph here of the investment, for example, it's really, we cannot predict what it's going to do after the final of the graph, but we can try to put these outputs in a neural network to try to predict the outputs for other instance of the time. And that's an application on stock markets. Here in medicine, we can use the neural networks. For example, if I enter the symptoms of a person, for example, chest pain, palpitation, cough, we can enter biochemical analysis, urine, blood, and other features of this person, the age, gender, or if this person smokes or is alcoholic. And the neural network is going to give us if diagnosis for some disease is positive, negative, or uncertain, for example. You can use this to identify tumors, for example, if this image has a tumor or not. And other application is for speech recognition. For example, if you call for a bank or other place that requires you to say out loud your CPF, for example, like 089, we have tools to do the neural network to learn this 1, 2, or 3 that I say and classify. That's the same thing as the images, but actually is with an audio. And basically there's many other applications, but I choose these 4 here. And that's it. Thank you for watching. I hope you have enjoyed. Questions? Okay.